I'll begin with a word prayer. Dearly Father, we thank you for this day. Thank you for these students. We pray that you would just help us to learn a little bit more about your creation today together. And I just pray that you just encourage the students to ask good questions as they think of the Lord. In your name I pray. Amen. I will use this. Sorry. I'll use this one. And I'll turn on this silly mic once I need it. I guess we don't need it quite yet. Maybe we do. Let's try it out. How about now? I guess that makes me a little louder. Okay, so just a few examples with numbers for your request. And so this is from lecture 4, which is posted, of course, on the course website. A certain race car travels 200 miles per hour as it races down a straight portion of track. How many feet does the car travel in 3 seconds? Well, this is like a 5th grade problem, right? But we should still be able to do it, right? So I take the constant velocity, 200 miles per hour, times the time. That gives me the change in position. All right, I successfully walked past that without feedback. And the real point of this question is, this example, is really just the unit conversion, right? So miles per hour, we can convert to feet per second by multiplying by these conversion factors, right? Like there's 5,280 feet in a mile. There's 3,600 seconds in an hour. So there you have it, 880 feet. All right. Don't mean to insult your intelligence with that example. I don't think I even have a WebAssign problem that easy. All right, here's another one. 2 friends, Bob and Hilbert, live in Zownsville. Of course, where else would they live? And they both plan to travel out of town, Interstate 30. The only rest stop is 130 miles away from town. Suppose Bob leaves at 1 p.m., travels at 65 miles per hour. Hilbert leaves at 1:15 p.m., and then he leaves. The question is, what speed does he need to drive to catch Bob at the rest stop? So when is Bob going to get to the rest stop? If it's 130 miles away, he's going 65 miles an hour, it takes him 2 hours, right? So basically what we have to do is just solve 130 miles, well there's the 2 hours, but here's math that I just used common sense to get it, but you could also derive it, what I just said. Sorry, I'm breathing into the mic. I'm trying not to. Anyway, so the question was, how fast does Hilbert have to travel? So he's got to travel the same distance in 1.75 hours, right? Because if it's 2 hours and he leaves 15 minutes later, that leaves him 1 hour and 45 minutes, or 1.75 hours. So the velocity for Hilbert is the change in position over the change in time. Oh man, that's right. I'm sorry. I have this like duller red one that I meant to bring, but it's in my office. I'm suffering with you. Sorry about your eyes. I mean, if you got sunglasses, you can put them on. It's cool. So 130 divided by 1.75, you have 74.29 miles per hour. So, seems reasonable. Of course, you should travel faster, right? Catch up. All right, moving on. I like this example. This example is a non-trivial application of the concept of average velocity. In here, by default, if I talk about velocity, I'm talking about instantaneous velocity, right? So just keep that in mind. But the concept of average velocity is still useful. So here's the problem. You got Superman. He's going a little bit slow because it's cloudy. So the warmth of the yellow sun is not having its full effect on him so well. And but he's flying back and forth at a speed of 500 miles per hour between 2 trains on a collision course. All right? You can imagine this. You got, oops, sorry, I didn't shine that in your eye, did I? Okay. So you have 2 trains, they're coming at a collision course, and Superman's flying back and forth from one to the other, like this. I don't know why I'm doing it. I think mostly for the purpose of this word problem. The trains have speeds of 80 miles per hour and 50 miles per hour, and they begin 150 miles apart. The question is, how far does Superman travel as he flies back and forth between the trains? I guess he's going back and forth fighting 2, let's say, ISIS, let's say, has people on both trains, and they're terrorizing, and they've got some kryptonite, so it's taking him some time. He's going back and forth from one train to the other, and it's taking him some time to take down the bad guys. Anyway, but of course, since we're filming this, it's going to take until the trains almost collide for Superman to finish his act of valor. And so the question is, how far does Superman travel as he's doing this, flying back and forth through the two trains on the collision course? And so if you think about it, what's going to be the deal? Well, if they're going at 80 miles per hour and 50 miles per hour, when are they going to collide? How long does it take for them to collide? Here's a way we can analyze it. So what I'm going to do is to find the time when the trains collide, I'm going to call the train A and the train B. The A is 80 miles per hour, the B is minus 50 miles per hour. Here's a picture. This one's going that way, that one's going this way. When does the collision happen? All right. The collision happens, of course, when they're both what? At the same position, right? So the initial position of A, I'm defining to be 0. The initial position of B, I'm defining to be 150. You can do this. You can choose a coordinate system to model what you're given. You guys with me so far? Then once I have that, I have equations of motion for both. The A train is 80 times t. The B train is 150 minus 50t. To find the collision, set them equal. And that will tell me the time. Now some of you intuitively knew that all you needed to do was assume that it was like they're going together at 130 miles per hour, right? And just take that 150 miles and deal with it. So some of you have some kind of intuition about relative velocities that is useful. But we don't have to have that intuition. We can just solve it brute force like I did here. And what we get is 1.15 hours, right? So since Superman is always traveling at 500 miles per hour because, these acts of courage as he touches the train happen instantaneously, he's immediately going back to the other one at 500 miles per hour after he saved the baby or cat or whatever it is. And so he's always traveling at 500 miles per hour for this whole 1.15 hours. And so Superman would travel 577 miles during this process. Now, if you actually tried to break this up into pieces and analyze each mode, like tried to analyze how many times is he flying back and forth, it would be quite complicated, right? As the trains approach, he's flying back and forth faster. Like, you'd have to calculate an infinite series of problems here to come up with this answer. But average velocity just does it like that. It's pretty neat. I like this example. It's sneaky. Questions? Feel feedback coming on. We derived this stuff last class. I won't go over it again. We essentially did that example last class and that one. This is a comment worth making. For constant acceleration motion, the average velocity is the average velocity. What do I mean by that? I mean that there's two notions of average velocity. The one is you can take the total, take the displacement divided by the time. That gives you average velocity, right? But on the flip side, you could look at, say, the velocity at time 1 and the velocity at time 2, right? And you could take the average of the velocities in the sense of, like, what's the average of 3 and 7? 3 plus 7 divided by 2, 5, right? That's a different kind of average than this kind of average, right? But fortunately, they're the same in the case of constant acceleration motion because of this little derivation right here. So it's sometimes useful to know that because you can say that the average velocity is the average of the final and initial velocities, and that gives you yet another way to attack kinematic equations. There is a select class of problems where you need to use this idea, and trying to do it the other way is much harder. For example, come on, where'd you go? Oh, by the way, oh no, is that it? Somewhere there's a picture here where there's something terribly, horribly wrong. Let me show you. Oh, here's the jerk example. We worked that last time. Here's a picture. a common conceptual misconception people have about physics is that if the acceleration is positive, the velocity has to be positive. Right? Or if the acceleration is negative, the velocity has to be negative. But the acceleration and the velocity, much like the position and the velocity, are not directly tied together. You can be going to the right while your acceleration is going to the left. That's braking, slowing down, right? And so one of the things here, so these all make sense. Like, if you're speeding up, your acceleration and velocity point in the same direction, right? If your car is braking, the acceleration points opposite the direction of the velocity, right? If the ball's thrown up, its acceleration is still going down, right? Because what goes up must come down. This one is harder to understand. Yeah? Does this make sense? The ball is dropping, its velocity is going up. This seems wrong, right? Let me fix it. If I was like a really good mathematician, magician, I could do that, right? And then it would actually happen. And then I would like put a thing over it and shake it off, and then you'd be like, whoa. And then I could go to Vegas. No, there's really no place for me in Vegas. It's okay. All right, so here's a pretty standard problem. We worked something like that last time. This is sort of the opposite version of the well problem. You throw a ball up, and then, well, you're going to get the start of the problem. Don't do feedback on me. Stop it. All right, so if we throw a ball vertically with a speed of 50 meters per second, what's the maximum height the ball gets to? And assuming the ball is thrown from 2 meters, then where the ground is y equals 0 meters. All right, so the final velocity, the velocity, right, is going to be v minus gt. Now the final velocity, if the top of the flight we're talking about, what's the velocity at the top of the flight?
0.
Right. So right before the marker comes back down, it has to stop. All right. So if to find the find the zenith of the flight, I can set the y velocity to 0, and so the time to the top is the initial velocity divided by g, 5.097 seconds for this one. So that will tell me what? That tells me how long it takes to get to the top of the flight, which was one of the questions which was asked. Then the other question is, how high does it go, right? So what I can do is I write down the kinematic equation for this case, which is y naught plus v naught t minus 1 half gt squared. Oh, actually, I don't know. The other question was how fast. Who was it? Oh, man. No, wasn't I given that? Yeah, I was given that. It was 50 meters per second. Sorry, I have a short memory. I forget what I was given. And I'm seeing green spots for some reason. But so the initial y position is what? It is 2. That was given. The initial velocity was, why am I doing this? Why did I do this stuff here? I mean, another way I could, I don't know, I'm not quite sure why I did this. I could have just done what? That's another way I could have found this 129.4. I could have plugged the time I just found, which was what? 5 point whatever. I could have plugged that into here and here, and just multiplied by the time and found this number the same way. But I decided to do some algebra instead to find it. Anyway, there it is, the max height, 129.4. And then to find the time of the flight in total, I have to solve this quadratic equation. 0, because 0 is when it hits the ground, right? So 0 is equal to y naught plus v naught t minus 1 half gt squared. And so I can solve for t by the quadratic formula as this. And you put in the numbers that you're given, and you get 10.23, which is a little bit more than double the top time. Why? right? Because it was thrown from a height of what? 2 meters. So there's an asymmetry here, right? Double the top time, where would the thing be? It would actually be back to here. This is when you're at twice the time the top time, right? No. All right. I advertised that there's a problem where we really need the. This problem's complicated. I'll let you read this one. This one's interesting. It's multi-step. Guy drops out of a plane, free falls, basically at 100 miles per hour, and then he opens the parachute, and then the rest of the way down 10 miles per hour. And the question, and there's a little bit more data given, and you're asked to find, how far he fell. I don't think I have anything quite that insidious in the homework right now. This two-stone problem is worth looking at. I'm going to skip past it though. Example 15. Let me just draw this. All right, so here's the problem. A certain subway car accelerates as it leaves the station. All right. It passes a certain person waiting for another train, and it takes 2 seconds for the first car, 1 second for the next car to pass. So in other words, it's a subway. It's a really strange subway car. It just has 2 cars. I don't know. I've never seen one with just 2 cars. I suppose it did. I suppose you can imagine these are just the first 2 cars, and there's another 20 past this or whatever. If you want to make it more realistic, whatever. So the person's standing there, and for the first car to pass, it takes 2 seconds. Understand? And then for the second car to pass, it takes 3 seconds. Understand?
Is it 3 for the first 2 or 3 for just the second one?
It takes 1 second for just the second one.
Okay.
So, like it says here. Now, I'm talking about absolute time over here, right? T equals 0, T equals 2, T equals 3. So there's the duration between this event and that event is 1 second. 1 second has elapsed between those events. Okay, so if the cars have a length of 10 meters, all right, how fast are they traveling as they begin to pass? Now, we are to assume that the subway car accelerates as it leaves the station, and we're going to assume that that acceleration is uniform. How do you solve this problem? Yeah?
Can it be just 0, depending on the acceleration? If it starts in front, like right at the guy, that's when it begins to pass. So it could.
Well, it doesn't seem like it's 0, see, because in fact it seems like there's a non-trivial acceleration, because from time 0 to time 2, you see 1 car past him. So from time 0 to time 2, the average velocity was what? 10 divided by 2? 5 meters per second. From time 2 to time 3, the cars have gone 10 meters again, but just in 1 second. So in fact, we've gone from 5 meters per second on the average over the first 2 seconds to 10 meters per second over the average for the last second. So it's definitely accelerating, given the data. Yeah.
Can you just use acceleration equals change in velocity over time?
Change in velocity over time. Maybe. Which ones would you use?
Find the 2 velocities and then find the difference between them.
So what would I guess my question to you would be, can you tell me how to find the velocity here at any time?
So the first one to pass, you would take, what the velocity would be 5 meters per second.
When would the velocity be 5 meters per second, would be my question.
The average is true.
That would not be true.
Is it constant acceleration?
I don't think the velocity, let me think about this one more. So here's a picture. This is V naught. Actually, I don't know it. But what I do know, here's 1 second. Oh, here's 2 seconds, right? And here's 3 seconds. I'm drawing a picture of time and velocity. See, the thing is, I know the average velocity from time 0 to time 2 is 5 meters per second. I think I could say the velocity, now I would agree with you that we could say, we could extrapolate from this that the velocity at time 1 is equal to 5 meters per second. I would totally agree with you about that. Would you agree? Like 5 meters per second, it's going faster than 5 meters per second right as the train reaches here. It's going slower than 5 meters per second over here. The average velocity is 5 meters per second over that time duration. With a uniform acceleration, the average velocity is equal to the instantaneous velocity at the mid-time. That's actually not a bad idea, though, because that wasn't too hard to figure out. What would can you tell me the velocity some other time? Like, if I believe that.
Would time 2.5 seconds be 10 meters per second?
Now, what's your reasoning there?
The same reasoning. You said the midpoint is the average velocity.
Oh, come on. No, they're not. Not assuming it starts from rest, no.
At time 2.5, at time 2.5 it should be 10.
At time 2.5, it should be 10 meters per second.
Yeah.
Yeah, I think that's right, because the average over this duration is what do we say, 10 meters per second, right? So at time 2, yeah, if you have 2.5 is, you say 10 meters per second. Now, let's use your idea. The acceleration is the change in velocity over change in time, right? Which would be what, 10 minus 5 meters per second. Let me skip the units here for a second. 10 minus 5, what's the change in time?
1.5.
2 minus 1, yeah, 1.5. So we get 5 over 1.5. Be careful, I should have units right as meters per second squared. So what is that?
3.3 repeating.
Was it 3 point?
3.3 repeating.
3.33333333333, roughly speaking, 3.33 meters per second squared. Right. Interesting. Very good, guys. Here's how I did in the notes. Rather different. Uh-oh. Oh no. What's 5/3? Uh-oh.
Not 3.3.
Oh, wait a minute, but what am I finding here? The initial velocity, which is not that. Sorry. Got some laser ricochet over here. So, yeah, what I do here is basically use that average velocity relation. So, like, the average velocity is the average of the velocities. The average velocity is the average of the velocities. The average velocity is the average of the velocities. I don't actually know V0, V1, and V2, right? But I think if I thought a little bit harder about this, I can get it. So you figured out it's 3.33 meters per second squared the acceleration, right? If that's uniform, we can work backwards from this one, right? So 1 second before it had 5 meters per second, it was at V0, right? So what's the relation between velocity and acceleration? So let's see here, V1 is equal to V0 plus the acceleration times 1 second, right? So V0 would be equal to 5 meters per second minus the acceleration times 1, which would be 3.33 meters per second. What's that give you? In other words, 5/3. So we agree. Now, this is a pretty good illustration of different solution techniques in here. You guys, each one of you had an idea about doing something with velocity, which was different than what I did, right? So which is the right solution? I mean, I don't know. My solution isn't that clever. I just used the I just use the average velocity thing 3 times because it's easy to think about, and then I do algebra. So I love algebra. So, anyway. That's bueno. We can agree or disagree. It's up to you. One more of these, and then I'm going to put this away, okay?
Wait, did you do it 3 times and then solve the system for these?
Yep. That's what I did. 3 equations, 3 unknowns.
Both methods give you an equal credit.
As a general rule of thumb, if you've ever seen any particular mathematical calculation before, we'll do that in here. So, pretty much. Here's another common question. 2 stones are dropped from a cliff. The second stone is 1.6 seconds after the first. All right? How far below the top of the cliff is the second stone when the separation between the stones is 36 meters? Read that again. 2 stones are dropped from a cliff. I label these stones A and B. Right? The one stone is dropped 1.6 seconds after the first. All right? Then it drops down, wait 1.6 seconds, drop another one. They're both dropped, right? That means that their initial velocities are 0. They're just dropped, right? Then the question is, how far below the top of the cliff is the second stone when the separation between the stones is 36 meters? So we're given that the distance between A and B is 36 meters at the point where we're interested in finding how far this is, right? How far below is the second stone from the top of the second stone, right? How far is the second stone below the top of the cliff at that time? So when faced with a question like this, I have to draw a picture, and I just have to write down everything that I'm given and try to think through it, organize my thoughts. Then I go to writing equations, which I know as we derived last time. Like, so one of the things I derived last time was this kinematic equation for constant acceleration. For B is the one that's dropped at time equal to 0, right? So for B, I'm saying time equals to 0 is when B is dropped, right? So for that, YB is Y naught minus 1/2 GP squared. By the way, I don't know what Y naught is. Y naught is the height of the cliff above Y equals 0, whatever that is, I don't know. I'm just going to call it Y naught. Why not? Sorry. It was there. I had to take it. So then, that's the equation of motion for B. The equation of motion for A is almost the same, except that it's so-called, it starts at 1 seconds afterwards, so instead of writing T here, I write T minus 1.6 seconds, so that's the equation of motion for this one, because it starts 1.6 seconds later. All right? So the time of flight for A is delta T, whereas the time of flight for B is just T. All right? So then what? What else do I know? What else am I given here? I'm given that YA minus YB is 36 meters. At some time I don't know. Right? So my goal is to find that time. So that's what I do. YA minus YB is 36 meters, that's given. But it's also equal to minus 1/2, G times T minus 1.6 squared plus 1/2 GT squared. The Y naughts are irrelevant. You could ask this problem for a cliff that's 500 meters tall or for a cliff that's 1,000,000 meters tall. It wouldn't change the answer, except that 1,000,000 meters tall would not be a reasonable height for a cliff on the surface of the Earth. I don't know, realistic physics example considerations. Anyway, so we do algebra. What I do is I divide G over here, and I FOIL this thing out. And what do? Hey, check it out. The T squared terms cancel. This is only a quadratic equation in appearances. In truth, it's a linear equation. I solve for T, I get 1.4936 seconds. And then I go back, I take this time, and I plug it back up into here, right? Well, actually, I plug it back into what? I plug it back into the A equation, because I'm interested in how far the A stone dropped, how far below the A stone was. when they're 36 meters apart, and there you have it, 10.94 meters. So, you see the thinking? What we do is we use the kinematic equations I derived last time, and we just plug in the data we're given, and we use algebra to find answers. You can't usually just write a formula down and plug in numbers. This is not a high school physics course. You have to analyze things. You have to understand the meaning of formulas and be able to apply them to various word problems. Let me put this away. I'm going to ask if we can have a different room. This is, this is not conducive to learning. It's certainly not conducive to me lecturing this fan. I'm going to ask. Can't hurt to ask, but we may not get anything from it, but I'm going to ask. So this moves us. Our next topic, of course, is projectile motion. Stop. Oh man, it used to do this thing, it stopped here, and then it went like back up like a foot, and then it came back down again, and then it went back up. But I used the force. Yeah, I don't know if you can tell that or not. That was the force. Of course, I'm, to be clear, I'm a mathematician. You only deal in absolutes. So, right. Way to use that. Sorry. It's not very accurate, actually. There's a lot of nuance in mathematics, but anyway. Projectile motion. Here's the deal. What is projectile motion? You take some object, some mass m, and you give it some initial velocity, say v naught, right? So the typical problem, and the thing that makes it projectile motion, and oh man, I've got to bring my props. All I got is here is markers. Oh well, here's some examples of projectile motion. Oh, that was not projectile motion. So the thing that makes these projectile motion is just that once the marker leaves my hand, right? Once I've given it the energy it needs to fly through the air, what assists it in its flight? Nothing, right? It's just flying through the air, and the force of gravity brings it back down. That's projectile motion. So if you got a rocket-powered bullet, or if you got a rocket, plane, parachute, these are not projectile motion. Projectile motion is very boring. In some sense, the simple equation that encapsulates it is that the acceleration is equal to, minus g times y hat. So mostly we're going to do two-dimensional examples, but sometimes I might do minus gz hat if I want to be three-dimensional and take z as the upward direction. All right. Sorry about that. So let's take the initial position of it to be x naught, y naught. Right? Then the equations of motion are what? Well, we have the acceleration is equal to minus g. Excuse me. The acceleration in the y direction, goodness gracious, acceleration is a vector. It's 0 minus g. So what's the, let's just get it all out here. So the y velocity is a function of time. Would be v naught y minus dt. On the other hand, the x velocity is a function of time. It's just what? The initial x velocity. All right. Now typically, when you think about projectile motion, you think about, shooting a cannon or launching an arrow or whatever, and you do it at some angle theta. All right? So typically the theta is given, theta is given the initial angle at which it's fired, all right? So like this. Like, hopefully I'm not getting cut off. All right, I didn't unplug anything. Yeah. All right. Lost. Okay. I think we're good. So in terms of theta, right, we can break down the initial velocity vector, and we have two things, right? We have this piece and that piece. So v naught y is v naught sine theta. V naught x is v naught cosine theta. V naught is the magnitude, it's the speed of a projectile as it leaves the gun, or whatever. So in view of that, these formulas simplify. This is v naught sine theta minus gt, and this is v naught cosine theta. All right? So far so good? What is the position as a function of time in the case of projectile motion? Well, integrate these velocities to obtain, what do we get? We get x, well, sorry, y of t is y naught, let's see here, plus v naught sine theta times t minus 1/2 gt squared. So that's y as a function of time. The x, on the other hand, is a little bit more boring. Or as my son would say, boring. So good. Sorry, it's kind of a household joke. But if you see my son, v naught cosine theta times t. So it's constant velocity of motion in the x, right? So, for example, it could look something like, this, I don't know, it starts here, and then so maybe we're thinking y equals 0 is the ground or something, and this is a flat plane. I don't know, you can add all kinds of things to this, right? So those are your basic equations that work for pretty much any projectile motion problem. A couple of really simple, very special examples. I'm trying to emphasize to you that these are special cases. So here's a special case, which is the problem where you begin and end at the same level. Suppose that you, well, let's dig a hole. And in this hole, we build a rail gun such that it launches a projectile, and you're doing it on the salt flats, which are totally flat, and we're neglecting the curvature of the earth, it's totally flat. And suppose you launch this, 3-ton, maybe it launches like a compact car or something, I don't know, some projectile, whatever you want. Something metal that a railgun could chuck up into the atmosphere. The question then, of course, is what's the range? What's this called the range, right? And that's for a given angle theta. So what makes this a special case is that the motion begins and ends at the same height. All right? And let's suppose that it's, initial velocity v naught. And let's see what formulas we can find for this. So in this very special case, we can ask the question, what's the, there's different ways to attack this problem. I'll ask, what's the time to the top? Yep.
When you said integrate the velocities to obtain those equations, you're using in the first one y of t, using y sub naught as the integration constant.
Oh, whoa, whoa. So you're saying I'm missing a plus x naught on this one, right?
Is that necessary?
Yeah, in general.
Okay.
But in practice, we could do something like,
You would make your initial 0 anyway.
yeah, like, okay, so that's a great question. To be lazy, let's suppose that x naught is equal to y naught is equal to 0 for this problem. But it's important to know that that goes there in general, especially for like asymmetrical motion, like the thing I was showing you earlier on the projector, the thing that was you threw the ball up from 2 meters. It's important to know that that 2 has to go with the formula. If you're also going to think about the ground, I mean, it has its place. So, but I'll tell you, I'm going to follow your lead. I'm going to say that x naught equals y naught equals 0 for this problem. In view of that, x is equal to what? X is equal to v naught cosine theta times time, right? And y is equal to v naught sine theta times time minus 1/2 gp squared. That's just for any time. Well, time greater than or equal to 0. Time less than 0 probably doesn't mean much sense physically, right? I would say this is for 0 less than or equal to t, less than or equal to boom. Now I've assumed that we've loaded the compact car with explosives or something. Or it's just a movie below a certain budget where everything explodes when it hits the ground. I don't know. Just pick it. So how do we get the time to the top, though? How about this? Vy at the top time is what? So by physical intuition, what's the velocity, the y velocity at the top?
0.
0, right? So that says what? That says that 0 is equal to, what is it equal to? It's equal to v naught sine theta minus gp times top time. So therefore the top time, the top, is v naught sine theta divided by g. Right? Now, by symmetry of the problem, what's the boom time have to be? It's got to be twice the top time, right? I can't do this in cases where it's not special. Like the reason I can do that is there's a symmetry between coming up and coming down in this problem. I can get away with this. In view of that, the range is what? Range is equal to x of twice the top time, right? Which is what? V naught cosine theta times 2 v naught sine theta divided by g. In other words, v naught squared sine of 2 theta over g. And there you go, that's the range formula. Move this stuff right through. What's another interesting thing you might ask about this problem? How about how high did it go? What's the max height? How would you find that? What's that? It's y of what?
T-top.
Yeah, y of t top. which would be what? It would be V naught sine theta times V naught sine theta over G, right? And then what? The minus 1/2 G times V naught sine theta over G quantity squared. Oh, check that out. Both of these are V naught squared. I've got V naught squared sine squared theta for both of these. And I got a G as well. Factor out G. So this gives me 1 minus 1/2. In other words, the formula for max height is V naught squared sine squared theta over 2G. So there you go, there's the max height for this projectile method. If you go back and look at the example I projected earlier, you can see that this formula is in play with theta equal to 90 degrees. And if we end up with like gt squared over 2, special case of this is what? You're just on the ground, right? And you just throw something up with velocity v naught. It goes to y is equal to 1/2, whatever 2, v naught squared. V naught squared divided by 2g, right? You just throw straight up. For example, if I threw something straight up with velocity, say 10 meters per second, how high would it go?
Divided by
5.1 meters if I was 10 meters per second. Okay, so let's see here. We can figure something out. I take this marker, right? And I throw it like that. It went about a meter. How fast did I throw the marker? Oh, well. How do we figure that out? It's at 1 meter, right? Equal to v naught squared over 2g, and then just solve for g. Solve for v naught, okay? So apparently I'm throwing the marker at what?
4.4 meters per second.
Square root of 2 times 9.8 basically.
About 4.4.
Sorry, I'm trying to not breathe in the mic, but I end up doing it. Ah. I like one of those dog collars. 4.42? Huh. Is that right? Funny. Oh, I was trying to compare it to 4.42 to the 5.1, which is just nonsense, right? I should be comparing 10 meters per second to 4.42. Duh. Thank you. Sorry we got such a late start today. I'm trying to fix this sound issue, but I'm not very good at it. So, you got to be careful with these formulas. These formulas only apply when? Special cases, right? When the initial height and the final height are the same. What's the maximum range? In this special case, 45 degrees, right? The biggest sine theta can be is 1. That happens when theta is 45 degrees. or minus 45 degrees. I mean, minus what? Well, I mean, obviously, you can either go like this, or you can go like that, right? Those will give you the maximum range. And the same thing is true for here, right? Well, no, actually, maximum height is what? When you put in theta equals to 90 degrees. You get maximum height. Of course, you probably should think twice before actually doing this. Yeah. You might want to start running. You did that. All right, let me look at another example here. So let's see, suppose you've got something like a building, and suppose the building is 100 meters tall, and you're throwing a basketball or something off it at an angle of 30 degrees with a speed of 20 meters per second. Where does it land? My question then is, where does it land? All right, so here's how we solve this problem. First of all, I would figure out what v naught x and v naught y are. So v naught, the x component of the initial velocity is 20 meters per second times the cosine of 30 degrees, right? The initial y is 20 meters per second times the sine of 30 degrees. All right? So that's respectively 10 meters per second. And what's the x velocity? What's 8.666? 8.666, I don't know. We'll look at it. 20 times cosine 30. 10 root 3. Thanks a lot. Calculated. 7.32 meters per second. Come on, Parker. 17.32 meters per second is the y velocity there. Okay, so now I have everything I need. By the way, I'm going to put, I'm just going to, for our convenience, I'm going to put the origin here. It's up to us. You control the horizontal and the vertical. You can put the origin wherever you want, but once you put it there, you got to deal with it. Once I do that, it's not such a bad choice though, because my x equation for the motion is what? It is 17.32t. My y equation for the motion is 100. Let's see here, plus 10t minus 4.9 t squared. Now I'm going to work in meters and seconds, okay? And then I'm going to put the units back at the end. You guys with me so far? Y minus 4.9. What's minus 4.9?
9.8
Yeah, 9.8 divided by 2 minus 4.9. So that's the 1/2 t2 squared. All right. So then at this point, I'm trying to find here, what do I know about that point? What can we say? That's where what?
Y equals 0.
Y equals 0, right? So what do I do?
Set y equals 0.
Indeed. So we have to solve 0 is 10, not this will be 100, plus 10t minus 4.9 t squared. Now how do you solve that? Yeah, I think Pythagorean theorem is not a bad option here. So t, Pythagorean theorem is the quadratic formula. I got Pythagorean theorem on the brain. Sorry about that. Minus 10 plus or minus square root of 100 plus 4 times 100 times 4.9. That's 4ac. Minus gives me plus. And downstairs, I got myself a minus 9.8. Oh man, come on. Where'd my calculator go? Ah, yeah. Hit it in plain sight. I always make a mistake in the execution of that formula when I'm hurrying. One of the things you might notice about this wonderful Casio FX 115 ES, which is the only one I can give advice for, it's the one I got. But you go to mode, and I go to equation. If I go to number 3, I can then put minus 4.9, 10, and 100. And it tells me
I think that's for
this formula will give me 5.652 or minus 3.611. One of these is extraneous, physically speaking. The minus 3.6 is what would happen if you were to follow this back as if it had been launched from the ground, only to reach this height under projectile motion. That's the physical significance of the minus solution. That's the one we're actually interested in. 5.652. And then how do you actually find where that is? Well, last but not least, we plug it back into x is equal to x, the final x is equal to 17.32 times 5.652. And that will give me meters for this coordinate. Now I gotta get out of this mode. Here in my mode, change my mode. 17. Yeah, so when it is 5.65. 97.9. Sorry about that. In other words, this is 97.9 meters, 0. There's where it hits the ground. Does that make sense? Now here's a question. What angle should I shoot that at with that given velocity as to maximize the range?
45.
Incorrect. 45 is for this guy. For this one, some other angle will maximize the range. So to actually figure that out, what you have to do, you'll put in 30, put in theta, and you will find x as a function of theta. Then you take the derivative with respect to theta, you set it equal to 0, and that will give you the maximum. And that's not a problem I can do in 3 minutes. So, I'm going to stop there. Thanks, guys. Sorry depriving you of precious class time with my audio visual nonsense.